In this video, we're going to look at the Jacobian matrix and suppose we have two functions say they're f1 and f2. So we have two functions of two variables. The Jacobian is defined this way. And I'll put a J in front to indicate Jacobian, though we don't have to use this. We define the Jacobian by taking the derivative of the first function and putting in the first row and the derivative of the second function in the second row. And then we take the partial derivative of the first function with respect to each of the variables. This is df1, df1 with respect to x and y, and then with respect to xy down here. So that would be the definition of the Jacobian if you have two functions that are functions of two variables. You do it like this. You have to always be sure to have the first function, the first row, second function, the second row, then take the derivative with each variable. And now it's good to keep it like x, y, or if you have like x, y, and x, it's good to keep in that order. Now you could also have the case where you have more than two functions. Now suppose we have three functions and they're each function of the same three unknowns. The Jacobian matrix is defined this way. Again, I'm calling it J. And again, it's going to be the derivative of the first function with respect to x, with respect to y, with respect to z, the derivative of the second function with respect to x, with respect to y, with respect to z, the derivative of the third function with respect to x, with respect to y, with respect to z. So it's always important when you're in the first row, you're working on the first function, second row, the second function, third row, third function, and you do the derivatives in order x, y, and z, x, y, and z, x, y, and z. So that's the Jacobian if you have three functions, all of the same three unknowns. So next, let's do an example. We're given three functions, f1, f2, f3, and they're defined here, x squared e to the y squared, z cubed, xy cos z, and then the x squared plus 4y quantity raised to the third power. And we want to find the Jacobian. And so let's go ahead and do that. And it might be good, at least at first, for us to at least quickly write down what we're going to do. We're going to take the first function in the first row, derivative with respect to x, with respect to y, with respect to z, derivative to the second function with respect to x, y, and z, derivative to the third function with respect to x, with respect to y, and with respect to z, like this. Now, I'm probably going to need a lot of room, so I'm going to actually do the derivative at the bottom of the page here. I think I'm going to need a lot of room because the functions are kind of wild. And so again, in the first row, what's the derivative of the first function with respect to x? So it's going to give us 2x. Then the others are kind of like constants. They're just kind of come along for the ride. So it's going to be 2x e y squared z cubed. Then derivative of this first function again. Remember, with respect to y, everything else is going to be constant. So this is going to be like 2. The 2 is going to go out in front. It'll be 2y when we take the derivative of that exponent. And so I'll call that 2x squared y. It'll look a little bit nicer that way. 2x squared y squared. And then, excuse me, e to the y squared z cubed, like this. And then we're going to take the derivative again of this function with respect to z. So we'll bring the 3 out front. 3x squared e y squared z squared, like that. So again, just double check, be sure this is right. Remember, this is derivative with respect to y. And this one was with respect to z. Then the derivative of the second function with respect to x, y, and z. And again, with respect to x, we're just going to be left with y cos z. The partial derivative with respect to y is just going to leave us with what? X cos z. And finally, derivative of this with respect to z. Remember, when we take derivative of the cosine, that gives us negative sine. So negative x, y, sine z. And finally, we go to our third function. Take the derivative of it along the bottom row. And so again, we're going to bring the 3 forward. We're going to use the chain rule. 3x squared 4y squared times the derivative of the inside with respect to x. Going to give us 2x. Again, do the chain rule again with respect to y. 3x squared 4y squared, then derivative to the inside with respect to y, going to give us 4. And you can kind of rearrange that to look a little bit nicer if you like. Finally, the derivative of this with respect to z. Now, there's no z's in the function, so that's just going to be a big 0. So that is our Jacobian for those 3 functions. Now, in other contexts, your functions might look a little bit different, especially if you're doing change of variables, something like you would do in, say, Calc 3 or multivariable calculus. So, for example, let me do an example here. So let's say if you have functions like this, where they're defined as x equal uv plus u, y is equal to 3u sine v plus EV squared. And now in this case, this would be, say, your first function. This would be your second function. So similar to before, except that this time your independent variables are u and v. So it's really important to recognize that your independent variables are u and v. And you can even think of x as being your function and y being another function. So if we want to find the Jacobian, then in this case, we could either name this F1 and F2 or name this G and H or whatever they sometimes do. Or again, you can just think of X and Y being your functions. And so we'll just take the derivative treating X and Y as our function. So that means, like we did previously on the first row, you're going to have your first function, second row, your second function. Though again, this time you want to take the derivative with respect to u and v. So it's going to be du dv, du dv like this. And so just like before, first function, the first row, second function, second row, the second function, the second row, take derivative with respect to u, then v, u and v. And so up here, derivative with respect to u is going to be 2v plus the derivative of that just going to be 1 over here, dx with respect to v, and that's going to be 2u. Derivative of that's going to be 0 with respect to v, so we can just leave off the 0. And then the second function, derivative of this with respect to u, that's going to be just 3 sine v. And then the derivative of this with respect to v, this becomes cosine, and that will be 3u cos v plus the derivative of this with respect to v, that'll be 2ve v squared, like that. And that would be the Jacobian in this case. Again, this would be a common technique that you'd need to use if you're doing change of variables. And if you have 3 functions, it follows the same form. If you have, like, say, a u, v, and a w, and here you have an x, y, and a z, you'll just have another row, another column, do derivative with respect to u, then v, then w. But it follows exactly the same form.